Good day, Dr. Bungay. We are Group 1 and Group 2 here to present to you the solution for the problem from example 25. The members of Group 1 are Hazelyn Go, Ralph Manlulu, and I, Alijaeh Go. The members of Group 2 are Naomi C, Victor Garcia, and Renzo Marcial. For example 25, the problem is as follows. Consider a steam power plant operating on the simple ideal Rankine cycle. Steam enters the turbine at 25 megapascal and 350 degrees Celsius and is condensed in the condenser at 75 kilopascal. Determine the thermal efficiency of the cycle if the isentropic efficiencies of the pump and the turbine are 80% and 85% respectively. Calculate the power output of the plant for a steam mass flow rate of 15 kg per hour. With our given simple ideal Rankine cycle, as illustrated here, we can establish the conditions from example 25. At point 3, where steam enters the turbine, there is a pressure of 2.5 megapascal and a temperature of 350 degrees Celsius. At point 4, where the steam is condensed in the condenser, there is a pressure of 75 kilopascal. This is isobaric cooling, so this means that the pressure at point 1 is equal to 75 kilopascal. For our required values, the first is the thermal efficiency of the cycle, as denoted by eta T, with the condition that the isentropic efficiency of the pump, or eta P, is 0.80, 80%, and the isentropic efficiency of the turbine, eta TU, is 0.85 or 85%. The second required value is the power output of the plant for a steam mass flow rate of 15 kg per hour.
Now let's obtain the thermodynamic properties of water at each point. Particularly at point 3, the problem has provided that pressure is at 2.5 megapascals and at a temperature of 350 degrees Celsius. Upon checking with the steam table, at this pressure, it has a temperature saturation of 223.99 degrees Celsius, which is lower than that of the actual or given temperature. Thus, we can conclude that at this point, water is a superheated vapor. With this, we can obtain the other thermodynamic properties. Specific enthalpy is at 3,126.3 kilojoules per kilogram, and specific entropy is at 6.8403 kilojoules per kilogram Kelvin.
Now at point 4, the given pressure is 75 kilopascal. Since there are no other given parameters, we can calculate the specific enthalpy at point 4 by obtaining the isentropic work and actual work done by the turbine. First, for the isentropic work, we assume that the efficiency of the turbine is 100%, which operates at constant entropy. As such, the specific entropy at point 4 is equal to the specific entropy at point 3, which is 6.8403 kilojoule per kilogram Kelvin. Based on the steam pressure table, steam is a saturated liquid vapor mixture at 0.075 megapascal. And here are the necessary parameters. From these, we can calculate the vapor quality by substituting the specific entropy of a saturated vapor and saturated liquid, given an entropy of 6.8403. As such, the vapor quality Y is equal to 0.9013. Now, using the vapor quality, we solve for the specific enthalpy at point 4 in an isentropic condition. Substituting the specific enthalpies, we obtain 2,438.10 kilojoule per kilogram. Now, using the specific enthalpy at point 3 and point 4, we can now calculate the isentropic work of the turbine, which is negative 688.20 kilojoule per kilogram. So next, using the given isentropic efficiency of the turbine, which is 85%, and the isentropic work of the turbine calculated, we can now solve for the actual work done by the turbine, which is negative 584.97 kilojoule per kilogram. From this, we can calculate the specific enthalpy at point 4 by getting the sum of the actual work and specific enthalpy at point 3. And the answer would be 2541.33 kilojoule per kilogram. From the steam pressure table and using our calculated specific enthalpy, we can say that steam is a saturated liquid vapor mixture at 0.075 megapascal. Here are the necessary parameters. The temperature at point 4 is equal to the saturation temperature of 91.78 degrees Celsius. Now, substituting the enthalpies in the expression, we can now calculate the vapor quality, which is 0.9466. And from this, we can also calculate the specific entropy at point 4 by using the given values in the table and the vapor quality. Hence, the specific entropy at point 4 is 7.1230 kilojoule per kilogram Kelvin.
At point 1, the condenser operates at constant pressure with the fourth point, making pressure 1 as 75 kilopascals or 0.075 megapascals. Additionally, the state of steam at the condenser is a saturated liquid. Therefore, from the pressure section at the steam table, we can obtain the values for temperature, specific enthalpy, and specific entropy, which are 91.78 degrees Celsius, 384.39 kilojoules per kilogram, and 1.2130 kilojoules per kilogram Kelvin, respectively.
Now, at point 2, the given that we know is that the isentropic efficiency of the pump is at 80%. Since point 2 is from a pump to a boiler, we can say that this process is an isobaric heating process, and it is a compressed liquid. We assume that the process is isentropic, where the entropy of point 1 equals to the entropy of point 2. It is also isobaric to point 3, so the pressure is the same, which is 2.5 megapascal. To further prove that the process is a compressed liquid, we find the actual entropy value of 2.5 megapascal in the steam table and find out that the saturated entropy is greater than the entropy from point 2. From here, we perform interpolation to find the closest isentropic temperature and enthalpy that relates to the entropy. Based on the calculations, we find that the isentropic temperature to be 92.04 degrees Celsius and the isentropic enthalpy to be 387.44 kilojoule per kilogram. Now, with our newfound values, we're able to calculate for the work isentropic by subtracting the H2 isentropic by H1 to get a value of 3.05 kilojoule per kilogram. With the isentropic work, we can calculate for the actual work by dividing the isentropic work with the isentropic efficiency of the pump, which is 80%. And the value that we got was 3.8125 kilojoule per kilogram. With the actual work, we can now calculate for the actual enthalpy at point 2 by subtracting the actual work with the enthalpy at point 1, which is equal to 388.2025 kilojoule per kilogram.
Now that we have determined the thermal properties at each point, we can now determine the thermal efficiency of the cycle and also calculate the power output of the plant. So firstly, we need to determine the specific work net, which is equal to the negative sum of the specific work of the pump plus the specific work of the turbine. So it is equal to negative 3.8125 minus 584.97. So it has a value of 581.16 kilojoules per kilogram. So for the thermal efficiency, it is equal to the specific work out over specific heat in, which is also equal to specific work net over specific heat at B. Now, specific heat at B can be determined by specific enthalpy at 3 minus specific enthalpy at 2. So the thermal efficiency is equal to 581.16 over 3,126.30 minus 388.20 times 100%, which has a value of 21.22%. So for the power output, It is equal to the specific work net times the mass flow rate. So 581.16 kilojoules per kilogram times 15 kilojoules per hour. So the power output is 8,717.35 kilojoules per hour. In summary, process 1 to 2 isentropic compression has a temperature of 91.78 degrees Celsius, pressure of 0.075 megapascal, specific enthalpy of 384.39 kilojoule per kilogram, specific entropy of 1.2130 kilojoule per kilogram Kelvin, and at a state of saturated liquid. For process 2 to 3, isobaric heating, it has a temperature of 92.04 degrees Celsius, pressure of 2.5 megapascal, specific enthalpy of 388.20 kilojoules per kilogram, specific entropy of 1.2130 kilojoule per kilogram Kelvin, and at a state of compressed liquid. For the process 3 to 4 isentropic expansion, it has a temperature of 350 degrees Celsius, pressure of 2.5 megapascal, specific enthalpy of 3,126.30 kilojoule per kilogram, specific entropy of 6.84303 kilojoule per kilogram Kelvin, and at a state of superheated vapor. And lastly, for process 4 to 1 isobaric cooling, it has a temperature of 91.78 degrees Celsius, pressure of 0.075 megapascal, specific enthalpy of 2,541.33 kilojoule per kilogram, specific entropy of 7.1230 kilojoule per kilogram Kelvin, and at a state of saturated liquid vapor mixture. And for the energy balance, we have the specific work of the pump, specific work of the turbine, specific heat at the condenser, specific heat of the boiler, specific heat in, specific work net, and also the thermal efficiency. So for the specific work of the pump, it has a value of 3.81 kilojoules per kilogram. Specific work of the turbine is negative 584.97 kilojoule per kilogram. Specific heat of the condenser is negative 2,156.94 kilojoule per kilogram. Specific heat at the boiler is 2,738.20 kilojoule per kilogram. Specific heat in is 2,738.20 kilojoule per kilogram. Specific work net is equal to 581.16 kilojoule per kilogram. And lastly is the thermal efficiency, which is 0.2122. And that's all for group 1 and group 2. Thank you.